Hello, welcome to our thermodynamic video on nozzles and pumps, certain parameters that will measure, specifically getting into enthalpic nozzles and pumps. Here, what we're going to be basing our premise on is the reversible steady flow work and the special cases where we can take the definition of specific work, that omega S, which equals the difference in specific enthalpies between the final conditions and initial conditions of our processes. Now, specific work, that's simply work divided by mass. It's a mass per mass amount for work. What I'm going to be showing you is essentially special cases where if you don't have a table of specific enthalpies, what can you replace H2 minus H1? Well, if we have a condition where we have constant density, then that difference of specific enthalpies can be replaced with the difference in pressures divided by rho, or the density of our material. And examples where that is relevant would be incompressible fluids, for example, liquids or even gases. Fluids, as in liquids. In the condition of constant temperature, the difference in specific enthalpies can be replaced with our gas constant times temperature times natural log of P2 over P1. And that's true for an ideal gas. When we have an isentropic process, what we can do is replace the specific enthalpic difference with the gamma factor times the gas constant times the change in temperature, T2 minus T1, over gamma minus 1. And if you do not have both temperatures at the beginning and end of a isentropic process, let's say you only have the initial temperature, but you have both pressures at the beginning and the end, well, then you can instead use this equation where the specific work, or the difference in enthalpic specific enthalpies, is gamma times R times the initial temperature divided by gamma minus 1, all multiplied by P2 over P1, the pressures, raised to gamma minus 1 over gamma, and then all of that in the brackets minus 1. Where students have often missed points is where they've forgotten to include that minus 1 outside of the pressure parentheses, but also forgetting to leave it in that larger set of parentheses, which I represent with a bracket right here. And where that would show up is for ideal gases with constant specific heats. Now, if we're not talking about a specific isentropic process, but just a general polytropic process, well then that would be our N index times R times the change in temperatures divided by N minus 1, or N times R times T1 over N minus 1 times the quantity of P2 over P1 raised to N minus 1 over N, and then that pressure ratio raised to that exponent minus 1. And that's true for, in general, an ideal gas. Just like if we had constant temperature of an ideal gas, we could use the second equation. Another situation is if we, say, have a few sets of information during an isentropic process, various pressures, volumes, and temperatures, we can connect all of those parameters together based off of the gamma index value. For example, P1 divided by P2, that's equivalent to the volume ratio V2 over V1, all raised to gamma. And that also equals the ratio of temperatures T1 over T2 raised to gamma divided by gamma minus 1. So if you have, say, both pressures and only one volume measurements, you can easily get the second one through this relationship. Or if you have, say, both temperatures and you need one of the pressures, you can do that as well. Now, for question 1, an incompressible water flow with a velocity of 1.5 meters per second enters a round circular nozzle with a diameter of 5 centimeters. If the outflow diameter of the nozzle is 2 centimeters, what is the outflow velocity? Well, think of this nozzle as the entrance, or where we're inputting our water, has a larger diameter of 5 centimeters and then tapers off toward the outflow end that has 2 centimeters in diameter. And the inflow has an initial V bar, or velocity, of 1.5 meters per second. And what we're calculating is the outflow velocity, V bar 2. Well, flow velocity is equivalent to the mass flow rate times the specific volume divided by area. Naturally, we have the same material flowing from the inlet to the outlet. Therefore, what you're going to notice is that the mass flow rate is constant, as well as the specific volume, or the inverse of density. Those are going to be a constant. Therefore, if we solve our velocity equation to leave mass flow rate and specific volume on one end, then we essentially have our initial and final conditions for velocity multiplied by area set equal to each other. So velocity 1 times area 1 equals velocity 2 times area 2. So solving for the final velocity, V bar 2, that would be the initial velocity times the ratio of area 1 over area 2, or the inlet area divided by the outlet area. Naturally, being a circle, those areas are going to be pi times the radius of that circle squared, R1 for the inlet, R2 for the outlet. And just to simplify our time, to avoid doing a conversion, instead of trying to take the radius, if we're already given the diameter, well then that would be, the radius is simply the diameter divided by 2, therefore the radius squared would be d squared over 4. And what's nice is, for both areas, when we take two areas divided by each other, that pi over 4 cancels out, and we're just left with the first diameter squared over the outlet diameter squared. And when two things are raised to the same power, you can put that ratio by itself, d1 over d2, raised to the same power. So our simplified equation, if you're comfortable with doing this quick setup, would be the outflow velocity equals the inlet velocity times the ratio of the inlet diameter divided by the outlet diameter squared. So in this case, just plug in what we have. Our inlet velocity, flow velocity, is 1.5 meters per second, and our diameters, since they're in the same units, it doesn't matter what units we use. So the inlet diameter is 5 centimeters divided by the outflow diameter of 2 centimeters. And then taking that diameter ratio squared, what we're going to be left with is our answer of a flow velocity of 9.38 meters per second as that water is flowing out of the nozzle. Question 2. We have air at 500 kilopascals and 350 Kelvin entering an adiabatic reversible nozzle. Adiabatic and reversible simply means this is an isentropic process. If outflow pressure from the nozzle is 200 kilopascals, what is the outflow temperature? And if necessary, your gamma factor for this material is 1.4. Isobaric heat capacity is 1.005 kilojoules per kilogram Kelvin, and our gas constant is 0.287 kilojoules per kilogram Kelvin. Essentially what we're given is our initial pressure and temperature, we know that essentially that the heat transfer rate is 0 because it's adiabatic and reversible, indicates that we're also isentropic. Our outflow temperature, our outflow pressure is 200 kilopascals. We're given our gamma constants, and we're just solving for the outflow temperature, T2. Using our isentropic relationships, but instead solving for T2 over T1, that comes out to that ratio of temperatures equaling pressure 2 over pressure 1 raised to gamma minus 1 over gamma. Therefore, multiplying by our initial temperature, our outflow temperature would be 350 Kelvin times the ratio of 200 kilopascal over 500 kilopascal raised to 1.4 minus 1 over 1.4. And if you plug in everything correctly, that would come out to 269.4 Kelvin. For question 3, we're dealing with a situation with our Bernoulli equation relating heat transfer for a controlled volume minus the work transfer rate or power of a controlled volume, CV. For question 3, air at 400 Kelvin has a flow velocity of 4 meters per second when it enters an adiabatic nozzle. What is the velocity at the outflow of the nozzle if the temperature is 390 Kelvin? And again, we have our various thermodynamic parameters relevant toward air. Well, our Bernoulli equation in this case is the heat transfer of a controlled volume minus the work transfer of a controlled volume equals the mass flow rate, m dot, multiplied by the difference in our specific enthalpies between the outflow and the inflow, plus the difference in our squared flow velocities divided by 2, essentially taking the average of the square of each velocity, plus our gravitational acceleration times the change in height. What this is showing is a relationship between enthalpy, kinetic energy, and potential energy of our air. Now, the nice thing about energy conservation in both nozzles and diffusers is plenty of our parameters in our Bernoulli equation actually drop out and become 0. Essentially, if we look at our nozzle in the image to the right, as air is flowing from left to right, well, the heat transfer and the work transfer are going to both become 0. So in reality, we have 0 minus 0. So 0 minus 0, I should say. Now, the change in height is very negligible in a nozzle and in a diffuser. So that Z2 minus Z1, that is essentially 0. So what we're left with is the difference in our specific enthalpies plus the average of the difference of our squared flow velocities. So in solving this equation, we have 2 different methods. They're both using a definition of specific enthalpy for an ideal gas. One of those is replacing H2 minus H1. We can use the isobaric heat capacity, specific heat capacity times the change in temperature, T2 minus T1. Therefore, that becomes 1.005 kilojoules per kilogram Kelvin multiplied by 390 Kelvin minus 400 Kelvin, which comes out to negative 10.05 kilojoules per kilogram. Now, as far as units goes, a kilojoule is a kilogram meter squared per second squared. So now we're just getting rid of the kilogram, and we're left with meters squared per second squared. To that negative 10.05 meters squared per second squared, we're going to add the average of our outflow velocity squared minus our inflow velocity, 4 meters per second, all that squared. And all that ends up equaling 0. So what we therefore have is, as we rearrange everything, we're going to have the square root of 10.05 times 2 plus 4 squared, or 16. Those units inside the square root are meters squared per second squared, so that ends up becoming meters per second, and our outflow velocity comes out to 6.01 meters per second. Now then, we have a second way to solve this by using a different replacement for the difference in specific enthalpies. Depending on what parameters you have available, we could also just use gamma times R times the change in temperature divided by gamma minus 1. And what that ends up being is 1.4 times 0.287 kilojoules per kilogram Kelvin times 390 Kelvin minus 400 Kelvin divided by 1.4 minus 1, which again comes out to negative 10.045 kilojoules per kilogram. Now, what we essentially get is our outflow velocity is still going to be the square roots of negative 2 times the difference in specific enthalpies plus the inflow velocity squared. And as we plug in everything, we're still going to get about 6.01 meters per second. Now, one thing I want to point out is in our main equation, because our heat flow and our power both become 0, even though we're multiplying by our mass transfer rate by this entire thing in bracket, basically it's 0 equals something times everything in brackets. Just dividing by the mass transfer rate gets us 0 divided by the mass transfer rate, and therefore the mass transfer is actually not important in this case because we can just divide it to the side that equals 0. That's why the mass transfer eventually disappeared. But you have two different ways to solve this equation. Actually, you have a few. But those are two very simple ones. Question 4, we have saturated water flow, or saturated water at a flow rate of 8 kilograms per second is pumped from 200 kilopascals to 1.6 megapascals. What power is required if the pump is 85% efficient? Essentially, what input power do you need to get this kind of scenario? Well, when it comes to pump efficiency, that's equal to the output power divided by the input power. How much power you get out of your pump divided by how much power you need to put into the pump to get it to run. Therefore, our eta, this will be a specific type of efficiency eta pump, which is equal to the power or the work transfer rate out of the system divided by the work transfer rate into the system. Now, using one of our definitions of work, the output power is going to equal the change in pressure times volume over time, which is the same as change in pressure times the volume flow rate, which then becomes the change in pressure times the mass flow rate divided by density, or the mass flow rate times specific volume. What we're using is essentially 1600 kilopascals, or that 1.6 megapascals times by 1,000, so that we're in the same units for pressure. 1600 megapascals minus 200 kilopascals. multiplied by 8 kilograms per second divided by the density of water, which is approximately 1,000 kilograms per cubic meter. In reality, it's more closer to 996, I believe, kilograms per cubic meter, but if you're not told it, you should be told specifically what density you're using, which if you're not, for water, treat it as 1,000 kilograms per cubic meter. Therefore, the output power becomes 11.2 kilowatts. Just be careful. If you're solving for the output power with these units, kilopascals, and then cubic meters per second, you're going to end up with kilowatts specifically. Now, going back to the thermal efficiency of our pump, well, the work efficiency, that would be the output work transfer rate divided by the input work transfer rate. Rearranging it to find the input power, what we find is 11.2 kilowatts divided by a pump efficiency of 85% or 0.85 comes out to an input power requirement of 13.2 kilowatts. Therefore, in order to drive this pump, whether you're burning gas or you're heating up water to form steam, you need in some way to input 13.2 kilowatts of power in order to convert that into 11.2 kilowatts of usable power for some process. Now, question 5. Air at a flow rate of 20 kilograms per second and 300 Kelvin and 180 kilopascals of pressure enters an isentropic compressor. Determine the power requirement to raise the outflow pressure to 2 megapascals. And of course, for air, we have our various thermodynamic parameters of gamma, isobaric specific heat capacity, and our gas constant. Well, our main equation here is the work transfer rate equals the mass flow rate times the difference in specific enthalpies. We don't have an access to a table for these specific enthalpies given these pressures and temperatures. However, we can replace H2 minus H1 with what is shown in brackets. Gamma times R times the initial temperature divided by gamma minus 1, multiplied by all of this in parentheses, pressure 2 over pressure 1 raised to gamma minus 1 over gamma. Also, that pressure ratio outside of that pressure parentheses, subtract by 1. And then that will be in the larger set of parentheses. And all of that was just spoken, the replacement for H2 minus H1, don't forget to multiply by the mass flow rate, either MFR or M dot, depending on your textbook or chapter. Therefore, the work transfer or the power will be 20 kilograms per second, all multiplied by 1.4 times 0.287 kilojoules per kilogram Kelvin times 300 Kelvin divided by 1.4 minus 1, further multiplied by 2,000 kilopascals. That would be the 2 megapascals converted to kilopascals, so that we're in the same units. A ratio of 2,000 kilopascals divided by 180 kilopascals raised to 1.4 minus 1 divided by 1.4, and be very careful. Also, subtract by 1. Common errors for this part of our chapter is either forgetting to subtract by 1 or not subtracting by 1 where it's appropriate, specifically when it comes to the pressure ratio. Be very careful. You take your pressure ratio, raise to that exponent, and then subtract by 1. Don't forget it. And what we end up getting is if we solve for our power using the units shown, then we're going to end up with kilowatts, 5,964 kilowatts. However, your question may ask you to give your answer in megawatts instead. Therefore, your initial answer will be in kilowatts, but divided by 1,000 when asked, and you'll get it in 5.96 megawatts. For our last question, air at a flow rate of 25 kilograms per second at 320 Kelvin and 160 kilopascals enters a compressor having an isentropic efficiency of 90%. Determine the power required to raise the outflow pressure to 2 megapascals, and if necessary, gamma is 1.4, isobaric specific heat capacity is 1.005 kilojoules per kilogram Kelvin, and our gas constant is 0.287 kilojoules per kilogram Kelvin. Now, we essentially have our same equation from the prior problem, but now we're thinking of isentropic efficiency. That means we're going to solve for an input power, but we can first solve for the output power, W dot output. There we go. So the output power, or the output work transfer rate, is the mass transfer rate times gamma RT1 over gamma minus 1, all multiplied by the pressure ratio P2 over P1 raised to gamma minus 1 over gamma, and then taking that ratio after raising it to that exponent power, subtract by 1. What we end up getting is 25 kilograms per second times the quantity of 1.4 times 0.287 kilojoules per kilogram Kelvin times 320 Kelvin divided by 1.4 minus 1, all multiplied by, again, keeping pressures in the same units, 2,000 kilopascals divided by 160 kilopascals raised to 1.4 minus 1 divided by 1.4, and then afterward subtracted by 1. Rounding it, this comes out to an output work transfer rate of 8,500 kilowatts, or 8,500 kilowatts. Now our isentropic efficiency, or eta S, equals the output work transfer rate divided by the input work transfer rate, or the output power divided by the input power. Rearranging it to solve for the input power, that would be our output divided by our isentropic efficiency. Therefore, 8.5 megawatts. Converting our 8,500 kilowatts to megawatts, usually when it comes to these types of systems, there's a lot of power, so we use megawatts. And if you're required to have your answer in megawatts, you'll be told specifically. So convert it to megawatts, 8.5 megawatts divided by an efficiency of 90%. An isentropic efficiency of 90% is 0.90. So that becomes an input power of 9.44 megawatts. And yeah, thanks for watching this lesson. As always, likes and subscribes are not necessary, but they're fun to see. And if you feel like it, maybe a comment will help a future class. As always, it's glad to have you all, and peace.